to spend some time today is how to figure out different priors that you might want to use in linear regression. So if you remember what we have done, we gave very weakly informative priors, right? We have our beta 0, beta 1, and sigma, I think. And at that point, we're saying that I really don't know where beta 0 is going to be. So we gave beta 0 a normal, I think, 0 and 100. So that's a very wide prior that we sort of let the data to decide where the beta 0 going to be. And then we also, I think we gave the same normal 0 and 100 standard deviation for beta 1 as well. So that is once again a weakly informative prior. And then we give 1 over sigma squared to be a gamma 1, 1. Okay, so we call this weakly informative. And that can be used when you really don't know where those parameters are going to be. And like I said, then you can let the data decide where you think the posterior should be. So the data is going to drive, I should say the model together with the data going to drive the posterior inference. But sometimes you might know certain things about, the data and stuff like that, that you want to give what we call maybe informative prior. Okay, so let's talk about 2 different ways to do that. And I think the last lab 5, is on practicing how to specify this kind of new priors that can incorporate your belief. Okay. So the first one that I want to introduce is what we call subjective prior. And to do that, we actually need to, first of all, standardize the data. And for those of you who have done standardization before, you know that for any data point, let's just say for yi, for the standardized version, we put a star next to it. So that would just be standardizing, meaning that we subtract the mean from each observation and divide it by its standard deviation. Okay. So you do that for the y's, you do that for the x's. In R, the scale function can do all that for you. So it will be pretty straightforward. Okay. And the standardization really just changing the values, I guess the range of values and everything on the x and on the y, but it doesn't really change the relationship between x and y. You see that here, the 2 plots on the left, we have the original scale. Okay, we don't do standardization. We are logging only, we'll only get the log. So the log expenditure on the y-axis being plotted against the log income on the x-axis, and that's how the data looks like. Okay. On the right-hand side, we did the standardization, and you can see that the log expenditure being standardized on the x on the y, and then the log income standardized on the x, and you see that there's no change in the shape or whatever of the relationship between the 2 variables. Okay, so standardization is in a lot of ways trying to make the model a little bit easier to fit, especially in the frequentist point of view. But for us, we introduced this mostly try to show you how you can actually give subjective prior. But then, of course, if you look at the range of the data, okay, originally we have 6 to 10-ish, I guess, on the y-axis, that's the log expenditure, and 6 to 12-ish on the log income. Okay, once you do standardization, things usually going to be centered around 0, and then going back, going up and down, like between 2 or 4 or 5-ish. Okay, so that's the main change, I would say. But once we do standardizations, things a little bit easier to interpret it. So let me show you one example. A standardized value, like I said, represents the number of standard deviations that the value falls above or below the mean. So if you remember what we did, we have our yi star equals to yi minus y bar divided by the standard deviation of y. Okay. So we first of all subtract the mean y bar from each observation yi, and then we divide that by the standard deviation sy. So the standardized value, the yi star itself, tells us the number of standard deviations. Either this yi is above the mean or below the mean. Okay, so that's why maybe in the past you have heard this kind of rule of thumb. After we do standardization, if an observation is like 2 standard deviations away from my mean, then that is a kind of like an outlier or unusual observation. Okay, so that's what we mean by, well, when you do standardization, the standardized value can give you the number of standard deviations above or below the mean of this yi. Okay, so with that, if I'm looking at xi star equals to -2, then I'm looking at this observation being 2 standard deviations below the mean of x. If I'm looking at yi star equals to 1, then this yi, the original value for this record, there's going to be one standard deviation above the mean of y. Okay. So this value gives you the number of the standard deviations. And this is how maybe the first time that you were introduced the z-score, that's the definition of z-score. Anyway, we do standardization so we can start to make the interpretation a little bit more straightforward, because now the standardized value represents the number of standard deviations above or below the mean. So if I have any particular belief about certain observations, then I can translate that into this setup. So if I now work on everything on the standardized version, okay, so I have my yi star, okay, and I have my mu I star over here, which is beta 0 plus beta 1 times xi star. So the star is because I standardize x, and because of that, my mean is standardized. And I also standardize y, so I put a yi star over here. So you can see that, well, the model, even though notation-wise looks very similar to what we had on the unstandardized data, but the beta 0 and beta 1, now the interpretation is totally changed. So for example, the intercept right now will be the expected standardized log expenditure for a consumer unit that has the average log income. So remember, the intercept, whenever we do it, is looking at when xi, or in this case, xi star equals to 0. And when xi star equals to 0, we're talking about an observation at the mean. Okay? So that's why we say this the average log income, where xi 0 equals to the mean. So if I have a particular belief about this kind of observation, then I can use subjective prior through the standardization process. Similarly, the slope over here is going to be the change in the expected standardized outcome, the log expenditure, when the standardized log income increases by 1 unit. In other words, we're talking about 8 observation increases by 1 standard deviation. Because 1 unit right now is at the standard deviation level. So that's how you can change all of the interpretation after doing the standardization. And like I said, if you have any strong opinion or prior belief about any of this, then you should be able to incorporate that into your prior. Once again, or I should say one more thing I want to mention is the slope beta 1 will equal to the correlation actually after you do the standardization. So if you have your data standardized it, whatever the beta 1 actually will equal to the little rho that you probably have learned in the past, the correlation coefficient. So beta 1, once you do standardization, also gives you a sense of whether the correlation is positive or negative. Okay. So this is some background, and then of course, as you know, correlation itself, the absolute value of the correlation indicates the strength of the linear relationship. Okay, so this is probably from your intro stats course in the past when you first learned linear regression. All right, so let's see how we can give a prior based on what we have talked about using standardization. So first of all, we're still doing the simple version of assuming independence. So I'm having independent prior for each of the 3 parameters. So the joint beta 0, beta 1, and sigma becomes the product of the marginals pi beta 0, pi beta 1, and pi sigma. So to give a prior on the intercept, so once again, if we believe a CU of the average log income, which is xi star equals to 0, will also have an average outcome, then what I can do is I'm going to give a normal prior center as 0 with a particular standard deviation as 0. And this is saying that, well, if I believe beta 0 going to be a 0, which is the mean, and then my S0 once again can control how confident we are. If we think beta 0 going to be really at value 0, then I can choose a small S0. But if I think, well, maybe I'm not very confident, I just think it might be around 0, so I can choose a larger S0 value. So that's for beta 0. And if you do that for beta 1, beta 1 is once again, as we know, it's equivalent to the correlation. So if you have very strong opinion about what the correlation value should be, for example, you can give it another normal center at mu1 with standard deviation S1. And the mu1 going to represent your best guess of the correlation because it's at the mean. Okay. And then S1, once again, represent the sureness of this guess. Okay, so I'm giving you an example over here. So for beta 0, we're using normal 0, 1. That is to say that, well, I think most likely beta 0 is going to be around 0 because I'm giving a relative small f0 value. And then for my beta 1, because beta 1 represents the correlation after standardization. So I kind of have a very strong belief that I think correlation is about 0.7. Okay. So then I can center it at 0.7, and then my 0.15 is a showing you, I guess, a relatively high confidence about this 0.7 guess. Okay. So all of this applies only after you do the standardization. So that's why we introduce standardization first. Because after you do standardization, beta 0 and beta 1, the interpretations start to change. Okay? Especially for beta 1, it is equivalent to the correlation now. So whatever prior belief that you have about the correlation, you can give it to beta 1, and that is a what we call subjective prior. So it's going to be representing what your own belief going to be. So MCMC wise, as you can see, we're going to do JAX once again. Okay. You need to do standardization first before you pass the data into that. But then after you do that, well, beta 0 follows a normal. We have seen how to do a normal, right? D-norm in JAX. Beta 1 follows another normal, and then you have those values that you want to put in. And of course, don't forget to give a prior for sigma, and then you should be ready to go for the rest of your inference. So I think I have some example over here. And let me just, we're using for sigma, by the way, I think standard deviation is always hard to give a informative prior in many cases. So if you don't know too much, I think giving a weakly informative prior will be fine. So to sum up, equations 29 to 31 gives us the 3 different independent priors that we're having for this subjective prior. But don't forget, this is done only after you standardize the data. Okay. So you should always standardize the data first and then pass it to JAX. And then the rest of the model string probably doesn't look quite different, but making sure that you transform the data in the first place. So the model string, like I said, wouldn't look too different. In fact, almost identical to what we had done before for the weakly informative prior. Okay? Because we still have our beta 0 inverse sigma 2. Sigma and everything. So this, I should say, is identical actually. To the previous JAX, the model string that we have done. But then the key over here is that for the next few steps, okay, we have to standardize the data. So you see here, we created the standardized version and then pass them as Y and X. N doesn't change, that will still be the number of observations. The prior that we talked about, the mu 0, S0, mu 1, S1, and all that, this get passed into this part, okay? And then you will run your JAX, and then you will get your posterior inference. So it's always a good practice, of course, to make sure that you fix the number of chains that you want to run. You make sure that what kind of parameters you want to monitor. So that is the tracking process. And then the adapt process, burn in, sample, and thin. So one of you were asking questions, I think, on the weekly check-in of how to determine thin. You can always start thin as 1, meaning that you're saving every draw. But after you have run your MCMC, you should check your, in particular, the autocorrelation plots to make sure that you don't have very high autocorrelation. If you do, then at whatever lag that the correlation starts to drop should be your thin value, and then you should run this one more time. Okay. So for us, I just want to show you, this is the JAX output. Overall, the effective sample size seems fine. Beta 0 seems to be, center around 0 and very small overall as well. And we got beta 1 and sigma and everything over here. Plotting wise, this is for beta 1. MCMC diagnostic seems fine and all that, right? So you'll be able to summarize your results. And so that will be the subjective prior, that if you have very strong belief, in particular about the correlation between the 2 variables, then I would suggest you standardize the data and then give beta 1 your prior belief about the correlation, and then now you can incorporate your prior belief in your model estimation. Okay, so that's one type. Okay, another type is what we call conditional means prior. You will see that we'll do this for lab 5 as well. And I want to give you an overview, and then whatever time is left, you can keep working on lab 4. or if you want to start on lab 5, I posted the files already, so you can take a look as well. So the two methods that we have talked about so far is the first one is the weakly informative, okay? That's being done on the original data. And just now we talked about the subjective or informative prior on the model on standardized data. And in particular, that is where you want to give the prior for the correlation and through beta 1, and then that can be done pretty quickly. There is another way, I should say there are many other ways, but one way that I want to mention is what we call the conditional means prior. And let me show you what we mean by that, okay? So this will also, once again, be done on the original data. And in particular, if you have beliefs about the expected response value conditioning on the specific values of the predictor variable, then we're going to call this conditional means prior. So let me parse that for you a little bit. So what we're saying on number 2, item 2 over here, is that, well, for any particular x value that I know, I think, so for example, if x equals to 10, I strongly believe that expected value for that y is going to be 5, something like that. Okay? So if you have prior belief in this kind of format, we call it conditional means, because it's going to be conditioning on the x value that you want. And it's called conditional means because we're trying to express our belief about the expected outcome. So that's the mean itself. Okay. So let me show you what we mean by that. So first of all, we're doing this independence, everything will be simpler. And the linear relationship is very familiar. At this point, we have mu I equals to beta 0 plus beta 1 times xi. That's the usual setup of what we have. Okay. So for conditional means prior, we can try to formulate prior belief or prior opinion about the mean values, mu I. So you will see that we're working on those mu i's. Okay? If you have mu I, once again, is the expectation of yi. Let me see that again. You know that mu I is the expectation of yi, and that's why we are, well, given a particular x that you believe yi should be what, then we can actually work out beta 0 and beta 1 in that way. So for example, for a particular predictor value xi, x1, let's just say, I think for mu1, if I believe mu1 going to be following a normal distribution with mean m1 and standard deviation s1. So what that means is that for x1, let's just say if it equals to 10 in our application, then the mean will be what? Mu1 equals to beta 0 plus beta 1 times 10, right? Because x1 equals to 10 in this case. And let's just say I believe mu1 itself follows this normal A2. So let me say that again. I have a particular x1 value that I'm interested in. Let's just say it equals to 10. Okay. And for that particular mean, for that particular predictor value, I think this mu1 is going to follow a normal distribution of 8 and 2. This is my first piece of my prior. Okay. And then I come up with another, predictor value, x2, okay? And let's just say my x2 equals to 15, okay? And I think when my x2 equals to 15, I believe the mu2 is gonna follow this normal 11, 2. So this is, once again, if you have a x value, and then given the x value, you think the mean gonna follow a particular distribution. In our case, we're using normal as illustration. Then this is what we mean by conditional means prior. Okay? It might still look pretty vague, but let me show you how eventually we can make it work. So the general idea, like I said, is you have a particular x value of interest, and then you think, given that x, my mu gonna follow another particular normal distribution. And then if I get two of them, I have both beta 0 and beta 1 as the unknowns, so I will be able to solve them because I have two equations and two unknowns. So let me show you what we mean by that, and then you will get the chance to do it, practice doing it for lab 5. But like I said, if we have mu1 and mu2, this is the two normals that I came up with earlier, okay? And then beta 0 and beta 1 are the priors that we're trying to give, okay? And if we're able to express beta 0 and beta 1 through this mu1, mu I equals to beta 0 plus beta 1 times xi, and then if I have all of my mu1, mu2, x1, x2, then equation 30 and 39, like I said, I have two equations, two unknowns, beta 0 and beta 1, so I can solve it. Okay. So what I'm trying to say is, I have my x1, I have my x2. So x1 in my first period, I also have my mu1. My second period, I have my mu2. And then of course, mu1 follows a normal, mu2 follows a normal, x1 and x2, they're given to us, or like they're known, like 10 and 15. So with that, we should be able to solve our beta 0 and beta 1. So beta 1 in particular is mu2 minus mu1 divided by the difference between x2 and x1. And then beta 0 is mu1 time minus x1 times the ratio of that beta 1 earlier. So this part is the math part, which if you do the algebra, I'm sure it will make sense to you. But in terms of coding, okay, which let me just say that when mu1, when x equals to 10, we think mu1 follows normal A2. When x equals to 12, we think mu2 follows a normal 11 and 2. So those were the pieces go into our model, or I should say prior specification. Okay, so let me take a moment to show you this part. So the model string, first of all, we have our sampling. So this looks no different from before. Okay, you have the loop. Okay, you have your yi follows a normal with mean beta 0 plus beta 1 times x, and then your inverse sigma 2. Okay, so that's no difference from before. But the priors now look different. Okay, so remember, we are not giving prior to beta 0, beta 1 directly, but we are giving prior for mu1 and mu2 directly. So I have my mu1 follows a normal, mu2 follows a normal. I still have my inverse gamma and inverse sigma and all that, that's all fine. But I have these two new equations because I was able to solve my beta 0 and beta 1 if I know my mu1, mu2, and x1 and x2. Right? So compared to before, so let me write this. I think previously, this whole part was directly beta 1 follows a d norm, and beta 2 follows a d norm. Okay, so that's what had done in the past, because we directly give prior for beta 0 and beta 1. Okay. However, for the conditional means prior, which is what we're introducing right now over here, is that we're not giving prior to beta 1 and beta 0 directly, because it's hard for me to think about what the priors for them. It's not as intuitive. However, if I have particular x values, in this case, 2 pairs, if I have an x1, if I know x1 equals to something, I think the mean gonna follow a normal. And then if I think x2 equals to something, the mean mu2 gonna follow a normal. So I have 2 unknowns, beta 0 and beta 1, right? But I have my mu1, mu2, x1, and x2. They're all unknown. With 2 equations, I was able to, from the previous slide, showing the mathematical equation for beta 0 and beta 1. Okay. So what this means is that we're not directly giving priors on beta 0 and beta 1, but rather we're giving prior through mu1 and mu2, because we might have beliefs about them. And then we are able to mathematically write out the equation for beta 0 and beta 1. And don't forget, it is still beta 0 and beta 1 comes into the mean. Okay, so that's why we need to have equations and express them, but then the prior is being specified for mu1 and mu2. Okay, so like I said, this could be new to many of you, and in many ways, I think might not be as intuitive. But lab 5 is devoted to working through, well, we show you the JAX script, but there are other things that you need to work out to figure out the entire MCMC estimation. So that's what lab 5 is about. It's only on the conditional means part, okay? Because for the subjective prior, we talked about once you do standardization, things flow pretty naturally. But for conditional means prior, in many ways, I think it's new and could be a little bit counterintuitive. So lab 5 is devoted for that. So you'll be able to get practice. And I think that's all I want to talk about today, because I know you're still working on lab 4. And now we release lab 5, which will be due in 2 weeks, because next week we have the exam and all that. So we're trying to have this due the week after. And so for the rest of today's lecture, feel free to work on lab 4 if you haven't done it already. Lab 4 is due, I think, on Friday this week. Or if you want to start on this lab 5, I posted the material already. So feel free to do that as well. Okay, so I'm just going to walk around and answer questions. And Yeah, right. Marcus is asking in the in the chat. So can you say what the scope for the exam is? So I think everything up to, let's see, so everything after the first midterm, and then up until the end of hierarchical modeling. Okay, so the linear regression that we're covering right now won't appear on the exam. Okay? But I would say the format itself will be very similar to what we have done in midterm one. Okay, so the take-home part will be mostly R programming, but now of course you should be able to do JAGs as well, because we have introduced JAGs in this in the second half, or between the first midterm and now. So the take-home, I think, will be focusing mostly on data analysis using R, and the in-class portion will once again be focused more on derivation. Okay. Yeah. But of course, I'm happy to answer specific questions, and I'll announce the scope through an email as well, just to make sure that everybody's on the same page.